Every camera, every seismologist, every headline was pointed somewhere else. The San Andreas, the Himalayan thrust belts, the subduction zones of Japan and Chile. These are the faults the world has been trained to fear. The ones that show up in disaster movies and news alerts. But while all of that attention was locked onto the usual suspects, something else was moving. Not a single fault, not a single fracture in a slab of rock. An entire continent was tearing itself apart, and in the last stretch of time, that tear let out a scream in the form of hundreds of earthquakes packed into weeks. This is the story of the East African Rift System, the deepest and longest active rift on the surface of the planet, and the violent swarm it just unleashed while the rest of the world was looking the other way. To understand why this matters, you first have to understand what a rift actually is, because it is fundamentally different from the faults that dominate public imagination. Most of the earthquakes people know about happen at transform boundaries, where two plates slide horizontally past each other, like the San Andreas Fault in California, or at subduction zones, where one plate dives beneath another, like the boundary that produced the 2011 Tohoku earthquake in Japan. A rift is neither of those. A rift is what happens when a plate is being pulled apart from the inside, stretched until the crust thins, cracks, and eventually splits into two separate plates, with new ocean floor forming in between. It is, in the most literal sense, the birth of an ocean, still in its earliest and most violent stages. The East African Rift System stretches roughly 6,000 kilometers, from the Afar region of Ethiopia and Djibouti in the north, down through Kenya, Tanzania, Uganda, and Malawi, all the way to Mozambique in the south. It is not one clee and crack in the earth. It splits into two major arms, known as the Western Branch and the Eastern Branch, which wrap around the ancient, stable core of rock called the Victoria Microplate, like two arms of a slowly opening jaw. The Western Branch cuts along the edge, of the Great Lakes of Central Africa, Lake Tanganyika, Lake Malawi, Lake Albert, some of the deepest and oldest lakes on the planet, filling basins that only exist because the crust beneath them has been pulled down and apart. The Eastern Branch runs through Kenya and Ethiopia, carving the dramatic escarpments and volcanic highlands that define the Kenyan Rift Valley, a landscape so distinct it can be picked out from space. At the northern tip of this whole system lies the point where the real story of this swarm begins, the Afar Triple Junction. This is one of the most geologically extraordinary places on Earth, the only spot on the planet where three active rift systems meet above sea level. Here, the Red Sea Rift, the Gulf of Aden Rift, and the East African Rift all converge, and the three plates involved, Nubia, Somalia, and Arabia, are slowly but relentlessly pulling away from one another. Because of this triple pull, Afar has some of the thinnest continental crust anywhere on Earth, outside of an actual ocean basin. In places, the crust here is already so stretched and thin that it more closely resembles young oceanic crust than typical continental rock. This is why scientists consider Afar a living laboratory, a real-time preview of how oceans are born. Because in a few million years, geologically speaking, the blink of an eye, seawater from the Red Sea is expected to flood into this lowland and create a new ocean, splitting the Horn of Africa away from the rest of the continent entirely. Not far from the epicenter of these recent swarms sits one of the rift's most extraordinary features, a place that makes the connection between earthquakes and molten rock impossible to ignore. Erta Ali, a volcano rising from the Danakil Depression in Ethiopia, hosts one of the only persistent lava lakes on the entire planet, a churning pool of molten basalt that has remained active in various states for well over a century. The Danakil Depression itself lies more than 100 meters below sea level, making it one of the lowest, hottest, and most inhospitable places on Earth, with surface temperatures regularly exceeding 50 degrees Celsius. This punishing landscape exists precisely because the crust here has been stretched so thin by rifting that magma sits unusually close to the surface, occasionally breaking through entirely. The presence of a long-lived lava, like this close to the epicenter of the recent swarms, is not a coincidence. It is physical proof that the entire Afar region sits atop a shallow, active, and continuously replenished magma system, the same system that fed the dike intrusion beneath Dauphin and Mount Fantal. This slow-motion continental divorce does not happen quietly. It happens through exactly the kind of violent seismic and volcanic activity that has been recorded again and again along this rift, and the region's history gives us a preview of just how intense these episodes can get. In August of 1989, a section of the evolving boundary between the Arabian and Nubian plates in Afar produced one of the most striking earthquake swarms ever documented on the continent. Over a period of just 48 hours, the ground released 25 earthquakes of magnitude 4.2 or greater, all of them shallower than 15 kilometers deep. Studies of that swarm later showed the quakes were the result of slip-along conjugate. Normal faults bounding a narrow trough called the Dobie Graben a textbook demonstration of what happens when crust this thin gets pulled apart too fast for it to stretch smoothly. The shallow depth of those earthquakes was itself a clue to what was happening underground, because such thin crust simply cannot host the deep earthquakes you find in more typical continental settings. And yet, in a strange twist that shows just how unpredictable this rift can be, the very same triple junction also holds the record for the deepest earthquake ever recorded on the African continent. On November 8, 1978, an earthquake of magnitude 4.9 occurred at a depth of approximately 62 kilometers beneath the Afar region, far deeper than the typical 10 to 25 kilometer range where most rift earthquakes occur. Researchers who studied this anomaly concluded it likely happened beneath an actively spreading segment of the rift and was probably tied to the movement of magma deep underground during an episode of rifting. In other words, this one deep, unusual earthquake was not a normal tectonic slip. It was a sign of molten rock forcing its way through the crust from below, part of the same process that is slowly manufacturing new ocean floor beneath the surface of East Africa. The East African Rift is not the only place on Earth where a continent is being pulled apart, but it stands out because it is doing so on land, in full view of scientists, rather than hidden beneath an ocean. Other rift systems exist, such as the Rio Grande Rift running through the southwestern United States, or the Baikal Rift Zone in Siberia, home to the deepest freshwater lake on the planet. But neither of those systems is progressing toward full continental separation the way East Africa is. The Baikal Rift is spreading extremely slowly and may never fully split the Eurasian continent, while the Rio Grande Rift has largely stalled in geological terms. The East African Rift, by contrast, is the only continental rift system on Earth actively transitioning toward becoming a new ocean basin, complete with the volcanic activity, crustal thinning, and seismic swarms that mark every stage of that transition. This is why geologists frequently describe it as a natural laboratory unlike any other, a place where the entire life cycle of ocean formation, from the first cracks in solid continental crust to the eventual flooding of a new seafloor, can be studied in real time rather than pieced together from rocks that solidified hundreds of millions of years ago. This connection between magma and earthquakes is the single most important thing to understand about why this rift behaves so differently from the famous strike-slip faults everyone else is watching. Along much of the East African Rift, earthquakes are not purely the result of two blocks of rock grinding past each other. Many of them are volcano-tectonic earthquakes, seismic events triggered by the movement of magma as it forces open cracks in the crust, a process geologists call dike intrusion. When magma pushes upward and sideways into a crack, it physically wedges the surrounding rock apart, generating swarms of small to moderate earthquakes that can number in the hundreds within a matter of weeks, unlike the sudden, singular rupture of a large fault like the Seismology. Andreas, these swarms tend to be prolonged, clustered, and directly tied to the churn of molten rock beneath volcanic centers scattered across the rift. This is precisely the pattern that played out in the most recent and most dramatic episode to hit this rift system, an episode that unfolded almost entirely outside the spotlight of global news coverage, even as it produced hundreds of earthquakes in a matter of months. Beginning in late September, a swarm of earthquakes struck the Awash Fantale area of Ethiopia's Afar region, nestled between two volcanoes, Mount Fantale and Dauphin, inside the Awash National Park. In the span of about 5 weeks, 17 earthquakes above magnitude 4.0 shook the region, rattling communities, and in some cases, causing severe localized damage. That alone would have been a significant seismic event by most standards, but it turned out to be only the opening act. Starting in late December and stretching all the way into the following spring, a second and far more intense swarm struck the same area. This time, the numbers were staggering. Over roughly 3 months, the region recorded 314 earthquakes exceeding magnitude 4.0, most of them clustered around Mount Fantale. To put that in perspective, that is more earthquakes above magnitude 4 in 3 months than many entire countries experience in a decade. As the swarm intensified, something else began happening that turned concern into genuine alarm. In early January, authorities began receiving reports of steam emissions rising from the slopes near Dauphin volcano, a sign that heat and pressure were building beneath the surface. Ethiopian geological authorities documented plumes of steam venting from the area, and out of caution, officials moved residents from nearby communities into temporary shelters. Just days later, the region was struck by a magnitude 5.7 earthquake at a depth of only 8 kilometers, one of the strongest events of the entire sequence. A shallow, powerful jolt consistent with rock breaking under the strain of magma pushing against it from below. What makes this swarm so scientifically significant is not just its size, but what it revealed about the underlying machinery of the rift. This was not random background seismicity. This was the surface expression of a dike intrusion event, magma physically working its way through the crust, splitting rock apart molecule by molecule as it forced a path upward. Events like this are essentially nature's demonstration of plate tectonics, happening in real time, compressed into a timescale short enough for a single generation to witness. Instead of taking millions of years to notice a few centimeters of separation, residents of the Afar region felt the ground shake hundreds of times as literal cubic kilometers of new material pushed into the widening gap between plates. Detecting and interpreting a swarm like this one relies on a combination of technologies that, together, give scientists a remarkably detailed picture of what is happening kilometers beneath the surface, invisible to the naked eye. Seismometers scattered across the region record the timing, depth, and magnitude of each individual tremor. And when plotted over days and weeks, these events often trace out a migrating pattern, moving gradually along a line which reveals the path magma is taking as it forces its way through cracks in the crust. Satellite-based radar interferometry, known as INSAR, allows researchers to measure ground deformation from orbit, detecting uplift or subsidence of just a few millimeters across enormous areas, technology that proved crucial in linking the Olduvino-Lengai eruption to the swarm that preceded it. GPS stations planted directly on the rift's surface provide continuous, precise measurements of how far apart the two sides of the rift are drifting, confirming those slow but steady spreading rates of a few millimeters each year. Together, these tools have transformed rift monitoring from a purely historical, after-the-fact science into something closer to real-time forecasting, giving authorities in countries like Ethiopia a genuine chance to issue warnings before a swarm escalates into an eruption, exactly as happened when steam emissions near Dauphin prompted the evacuation of nearby residents. This kind of magma-driven unrest is not confined to Ethiopia's Afar region. It defines huge stretches of the rift's more volcanically active zones. Researchers studying the calderas scattered along the main Ethiopian rift and the Kenyan rift have documented widespread signs of unrest, consistent with the recharging and reorganizing of shallow magma reservoirs sitting beneath these volcanic systems. Temporary seismic monitoring networks deployed across these calderas have recorded thousands of small-magnitude volcano-tectonic earthquakes, most too small to be felt by people on the surface, but clearly visible to sensitive. Instruments, along with distinctive low-frequency seismic signals associated with the movement of fluids, whether magma, gas, or hydrothermal water, deep underground. At the Korbeti caldera in Ethiopia, ground uplift exceeding 6 centimeters per year has persisted for over a decade, a sustained swelling that gravity measurements suggest is being driven by a genuinely high flux of magma accumulating beneath the surface. Similar patterns of deformation, though varying widely in scale, have been documented at multiple calderas across the rift, painting a picture of a system that is not dormant in the slightest, but is instead continuously being fed by rising magma at a pace unusual for continental volcanism. Further south, along the Tanzanian portion of the rift, similar processes have been documented in connection with some of the region's most iconic volcanic features. Researchers have linked magma-driven earthquake swarms to the triggering of eruptions at Olduvino-Lengai, a volcano famous for producing the coolest and most unusual lava on Earth, a nitrocarbonatite lava so different in composition from typical basaltic lava that it flows at temperatures low enough to be black rather than glowing red, and solidifies into rock that dissolves in humid air within weeks. Studies combining satellite radar measurements of ground deformation with ground-based observations and elastic modeling found a direct relationship between an earthquake swarm and the subsequent eruption of this volcano in the mid-2000s, demonstrating a pattern seen again and again across the rift. Seismic unrest as the herald of volcanic activity, not a separate phenomenon, but two faces of the same underlying process. This brings us back to the present and to the wider seismic zone that has continued to generate headlines even after the major Ethiopian swarm began to quiet down. In January of this year, a magnitude 5.4 earthquake struck near Mbumi, Tanzania, another reminder that the borders where the Victoria and Rovuma microplates meet the larger Nubian and Somalian plates remain among the most seismically active zones on the entire African continent, with normal faulting earthquakes, the kind produced directly by the stretching of the crust, occurring on essentially a monthly basis along these boundaries. Further north, the region around Djibouti has continued to register moderate but persistent seismic activity, including events in the magnitude 4 to 6, range clustered along the same complex web of rift faults that feed into the Afar triple junction. GPS measurements across the rift show the plates here separating at rates of roughly 1 to 4 millimeters per year, a pace that sounds glacially slow until you remember that this stretching has been ongoing, essentially without pause, for more than 25 million years, and shows no sign of stopping. What ties all of these individual events together, the 1989 Dobie-Graben swarm, the anomalous deep 1978 earthquake, the sprawling 2024 and 2025 Awash Fintal sequence, the recent Tanzanian and Djiboutian tremors, is that they are not isolated disasters. They are chapters in the same continuous, ongoing process of continental breakup. Unlike a single catastrophic rupture on a fault like the San Andreas, which can lie dormant for a century before releasing centuries of accumulated strain in seconds, the East African Rift releases its strain in a completely different rhythm, near constant background seismicity punctuated by intense magma-fueled swarms that can deliver hundreds of moderate earthquakes across weeks or months. It is, in a sense, a slower but far more relentless kind of violence, one that never fully goes quiet, because the driving force behind it, molten rock rising from deep within the mantle, never stops pushing. Beyond the immediate danger of shaking ground and volcanic hazards, the rift also carries enormous economic weight for the nations that straddle it. Geothermal energy, heat harvested directly from the same magma systems responsible for these swarms, already powers a significant share of Kenya's electricity grid, making Kenya one of the largest geothermal energy producers in the world relative to its size. Ethiopia has similarly invested in geothermal exploration around calderas like Korbeti and Aludo, aiming to convert the same volcanic unrest that generates earthquake swarms into a stable, renewable source of power for a rapidly growing population. This creates a genuinely double-edged relationship between these nations and their rift, the very geological. Restlessness that produces destructive swarms and dangerous eruptions is also the source of a clean energy resource with the potential to transform national power grids. Understanding the rift, then, is not only a matter of hazard mitigation, but also of resource management, making the science discussed here directly relevant to infrastructure planning, energy policy, and long-term economic development across East Africa. This raises an obvious question. Why does this matter to anyone outside the region? The answer lies in both science and human safety. Scientifically, this rift is one of the only places on Earth where researchers can study the earliest stages of ocean formation while it is actively happening, rather than trying to reconstruct it from ancient rock records millions of years after the fact. Every swarm, every dike intrusion, every deep and unusual earthquake adds another data point to our understanding of how continents fracture and how oceans are born, knowledge that helps refine hazard. Models not just for East Africa, but for rift systems and volcanic regions worldwide. From a human safety perspective, the stakes are far more immediate. Tens of millions of people live along this rift, in cities like Addis Ababa, Nairobi, and Dar es Salaam, and in countless smaller communities scattered across the Ethiopian highlands, the Kenyan Rift Valley, and the shores of the Great Lakes. For these populations, understanding whether a swarm of earthquakes is a routine tectonic adjustment or the prelude to a volcanic eruption is not an academic exercise. It is the difference between staying home and evacuating, as authorities in the Afar region chose to do when steam began rising near Dauphin volcano earlier this year. Consider the sheer disparity in coverage against the sheer disparity in activity. A single magnitude 6 earthquake on a well-known transform fault near a major city can generate weeks of global news coverage, in-depth documentaries, and years of retrospective analysis. Yet the swarm near Awash Ventale, which produced more than 300 earthquakes above magnitude 4 in a single 3-month stretch, alongside a magnitude 5.7 event and visible volcanic steam emissions, received only a fraction of that attention outside specialist circles. This is not a criticism of any single newsroom or scientific body. It is simply a reflection of where infrastructure, population density, and media resources happen to be concentrating. But it does mean that some of the most scientifically important tectonic activity happening on Earth right now unfolds largely outside public awareness, tracked carefully by a relatively small community of volcanologists and seismologists, even as it reshapes the geological future of an entire continent. The East African Rift also serves as a sobering reminder of how selective public attention can be when it comes to natural hazards. Earthquakes along famous transform faults dominate headlines and disaster preparedness campaigns largely because of where large, wealthy media markets happen to sit, not necessarily because those faults are more dangerous or more active than rift systems like this one. In terms of sheer earthquake frequency, few places on Earth can rival the seismic intensity of the Afar Triple Junction and the broader East African Rift during an active swarm. Hundreds of magnitude 4+ earthquakes in a mat. Terror of months is a rate of activity that would dominate global news cycles for weeks if it happened along the California coast. Instead, because it occurred in a comparatively less monitored, less covered part of the world, it unfolded largely outside the awareness of the very people who study earthquakes for a living, until researchers specifically tracking the region began compiling the data and realized just how extraordinary the sequence had been. Looking ahead, scientists expect this pattern to continue, and in some ways to intensify as the rifting process marches toward its ultimate conclusion. The consensus among geologists is that the Afar region and the broader East African Rift are not simply cracking. They are actively manufacturing new oceanic crust beneath the surface, segment by segment, swarm by swarm. Some models suggest that within the next 5 to 10 million years, the Horn of Africa, encompassing Somalia and parts of Ethiopia, Kenya, and Djibouti, will separate entirely from the rest of the continent, with the Red Sea and Gulf of Aden flooding southward to create an entirely new ocean basin. On a human timescale, that future feels impossibly distant. But on a geological timescale, 10 million years is nothing, a brief final stretch in a process that began tens of millions of years ago and has already produced the deep rift valleys, towering volcanoes, and vast lake basins that define this landscape today. Every swarm like the one that struck Awash Fintale, every deep anomalous earthquake like the one recorded in 1978, every steam plume rising from Dauphin, is a small but measurable step toward that eventual outcome. It is worth remembering that our understanding of this rift is itself a relatively recent achievement. The idea that East Africa's chain of lakes, volcanoes, and escarpments formed a single, continuous rift system was first proposed by the British explorer and geologist John Walter Gregory in the late 19th century, after he traced the dramatic cliffs and valley floor of what is now the Kenyan Rift Valley, and recognized that it could not have formed through erosion alone. For decades, his theory remained a geological curiosity, difficult to confirm without the tools needed to measure crustal movement directly. It was only with the rise of plate tectonic theory in the mid-20th century, followed by satellite geodesy and dense seismic networks in the decades since, that scientists could finally confirm what Gregory suspected: that this valley was not a static scar left by ancient rivers, but an active wound in the crust, widening year by year. Every swarm recorded today adds precision to a theory that began as not much more than the observations of one determined explorer, walking the rim of a valley he could not fully explain. What makes this story worth telling right now is not just the scale of the recent swarm, though hundreds of earthquakes in a matter of months is remarkable by any standard. It is the reminder that our planet's most dramatic geological processes do not always announce themselves through the dramatic, single, headline-grabbing rupture that Hollywood and popular imagination have trained us to expect. Sometimes, the most profound tectonic event unfolding on Earth right now is not a single sudden fault rupture, but a slow, grinding, relentless tearing marked by hundreds of smaller earthquakes, rising steam and molten rock quietly working its way toward the surface, mile by mile, year after year, largely unnoticed by a world watching somewhere else entirely. The East African Rift does not need a single catastrophic earthquake to prove its power. It has been proving it continuously for millions of years. And the swarm that just shook Ethiopia, layered on top of the tremors in Tanzania and Djibouti, is simply the latest chapter in an ongoing planet-scale process that will, one day, quite literally redraw the map of Africa. If this kind of deep Earth science fascinates you, the story of our planet's slow, violent transformation is only just getting started, and there is far more happening beneath our feet than most people ever realize. Hit subscribe so you don't miss the next chapter in this ongoing series. Drop a like if you want to see more deep dives into the hidden forces reshaping our world, and leave a comment below telling us which geological mystery you want us to uncover next. The ground beneath us is never as still as it seems, and we'll be here to keep tracking every tremor,